In this video, we'll go over the homework that follows the lecture introducing the Taylor and Maclaurin series. And this homework will have two parts, one for Taylor and one for Maclaurin. So before we jump right into the homework, I just want to say that I hope that you watched this lecture. And now we can take a look at the first part of the homework. And the question here is to find the first four non-zero terms of the Maclaurin series. And the way we're going to do that is by recalling the formula for the nth term. So let me remind you what a Maclaurin series is. It's a series obtained from some function. It is centered at 0, and the nth coefficient is computed using this formula. So we take the nth derivative evaluated at 0 and divide it by n factorial. So this is what we call the Maclaurin series. And to find the first four non-zero terms, here's what we're going to do. We're going to start with the function. And we're going to evaluate this at 0. And we're going to conclude that A0 is f of 0 divided by 0 factorial. So it's just 0. Next, we're going to find the first derivative. It's going to be cosine of 4x to the power 4 times the derivative of 4x to the 4, which is 16x cubed, and we're going to evaluate the derivative at 0, which is going to be 0 again. So A1 will be zero. I have a feeling that a lot of first terms will be equal to 0 here. So for the second derivative, we have to do the product rule. So derivative of cosine is negative sine 4x to the power 4 times 16x cubed times the derivative of the second part, which is 48x squared, plus cosine. Actually, what am I doing here? We don't do the derivative. We're using the product rule. Now for the second one, it's going to be cosine of 4x to the 4 times the derivative. So this is also going to be equal to 0. So A2 is also equal to 0. And this is not the best problem to do by hand, so let's strategize here. Instead of doing this by hand, which we kind of have a clear path, but the problem is that all up to the 8th coefficient will be equal to 0, so I'm not going to find all these 8 derivatives, but we're going to strategize here. So we're going to look up a Maclaurin series for sine of x, which was shared to us in the lecture along the way. So right over here. And we're gonna use that as a starting point. So we know, this is a fact, that the Maclaurin series for sine of x is this. And goes from 0 to infinity. And now, if we're looking for the Maclaurin series for sine of 4x to the 4, well, we just need to replace x with 4x to the power 4. So the truth is that this holds for anything, any input. So if you take your input to be 4x to the power 4, then this is what we get. Sine of 4x to the power 4 will be equal to this. Maybe I was wrong about all of them up to a 8, but let's see. So now we can simplify this expression inside of the large sigma, and we have 4 to the power 2n plus 1, x to the power 8n plus 4 divided by 2n plus 1 factorial. So this is what the general formula looks like, but we are looking for the first 4 terms. So when n is equal to 0, what do we have? We have 1 times 4 times x to the power 4 divided by 1 factorial, plus when n is equal to 1, we get negative 1, 4 to the power 3, x to the power 12 divided by 3 factorial, and let's just continue. When n is 2, we get again 1 times 4 to the power 5, x to the power 20 divided by 5 factorial, and the fourth term will be negative 1 times 4 to the power 7, x to the power 28 over 7 factorial, and so on. So let's go ahead and enter this answer. And I really want to see what the solution looks like to this problem. We're not trying to simplify anything, just entering it as is. So I'll keep the factorial symbol here. And I'm going to just copy and paste this term. And let's see if that's the right answer. Of course it is, but let's see what the solution is. Right, so the solution is what we ended up doing, but at the same time you should be able to compute all those coefficients by hand. Or at least you should be able to understand that this is how this series is obtained, by manually computing all those coefficients. So let's go ahead and go to the next problem. We have a new function and find first 4 non-zero terms. Again, we can do it by starting with a function. Let's maybe try first few of them. F of x is ln of 1 minus x to the 4. F of 0, it's ln of 1, so it's 0. So a0 is just 0 over 0 factorial, which is 0. Now the first derivative is 1 over 1 minus x to the power 4 times negative 4x cubed. And now we evaluate the derivative at 0. We get another 0, so the first coefficient is also equal to 0, and so on. So we have to keep doing this until we get to collect the first 4 non-zero coefficients. Now, an alternative way will be to take a look at the table of Taylor and Maclaurin series, and in that table look for this identity. Actually, this is not the best one here. Ln of x is this. But we don't have x, we have 1 minus x to the 4. So we're going to replace that. And if we set this to be equal 1 minus x to the 4, we'll get ln of 1 minus x to the 4 being equal to the following expression. And 1 minus x to the 4 minus 1 is just negative x to the 4. And this can be further simplified. We can take out the negative and combine the negative ones all together like this. And now we're going to write the first 4 terms. So when n is equal to 1, we'll have negative 1 times x to the power 4 divided by 1. When n equals 2, we'll get... Actually, here's something interesting going on here. Negative 1 raised to an odd power is always going to be negative 1, so we don't need all that. We can just put negative in the front here. So we end up with negative x to the power 8 over 2 plus negative x to the power 12 over 3 plus negative x to the power 16 over 4, and so on. So this is our series. Negative x to the power 4, negative x to the power 8 over 2, negative x to the power 12 over 3, negative x to the power 16 over 4, etc. All right, so problem number 3. And once again, I am going to attempt to do the right thing here. And the right thing is to compute the coefficients one by one. So we start off by taking the function and then evaluating function at 0. So at 0 it will be equal to 2. So the 0th coefficient will be 2 divided by 0 factorial. 0 factorial is 1, by the way. And the answer is 2. Now we take the derivative. It's going to be 2e to the power 4x cubed times 12x squared. And we evaluate the derivative at 0. And we get 0. So the first coefficient will be 0 divided by 1 factorial, which is 0. And here, for the second derivative, we're going to end up with using the product rule. And very likely the second coefficient will be equal to 0. But the point is, this is how we compute all of these coefficients one by one. Now, a nice shortcut will be to actually recognize that the e to the x can be expressed like this. This is what we call the Maclaurin series for e to the x. And however, the x part, it's arbitrary, anything could go in here. And we're gonna choose that star expression to be 4x cubed. And of course, if you have number 2 here, you will just have an extra 2 over here. So, replacing the star with 4x cubed will give us the following expression. And this 2 can be also written inside. So we have 2 times 4x cubed to the power n divided by n factorial. And I'm going to simplify this just a bit. We have 2 times 4 to the power n, x to the power 3n over n factorial. But using also the properties of exponents, we can express that 4 as 2 squared, so we have 2 to the power 2n plus 1. X to the power 3n, all that divided by n factorial. So to write the first few terms, we're going to plug in n equals 0. So we have 2x to the power 0 divided by 0 factorial plus 2 to the power 3 x to the power 3 over 1 factorial plus 2 to the power 5 x to the power 6 over 3 factorial plus 2 to the power 7 x to the power 9 over 4 factorial, etc. So 2 plus 8x cubed plus 32 over 6 x to the power 6. And again, nobody's impressed here with me doing simple math, so I'm just gonna write it as is without trying to simplify anything, and that should be the answer. And this is how we make mistakes. Let's see, when n equals 3. Oh my god, I missed a factorial here. So this should be 2 factorial. This should be 3 factorial. So here we have 32 divided by 2, which is 16. And here we have 3 factorial, which is 6. And that's correct. So this was number 3. Let's do number 4. It will be very similar. This time I'm not even going to try to do the right thing. I'm just going to jump right into this shortcut. If we know we have e to some power, then the Maclaurin series for this function is this. Now if you have a number 3 here, that number 3 will just transfer over here. And now if we set the star to be 4x to the 5, here's what we get. On the left side we get 3 times e to the power 4x to the 5. On the right side we have 3 times 4x to the 5 to the power n, all divided by n factorial. Simplifying this will give us 3 times 4 to the n over n factorial x to the power 5n. So the first term of this series is 3 times 4 to the power 0 over 0 factorial times x to the 0 plus 3 times 4 to the power 1 over 1 factorial x to the power 5, 3 times 4 to the power 2 over 2 factorial x to the power 10, and the fourth non-zero term will be 3 times 4 to the power 3 over 3 factorial x to the power 15, etc. So the answer is 3 plus 3 times 4 over 1 x to the power 5. I'm just going to use this as a template. Oh, okay. 3 times 4 to the power 1 over 1 factorial times x to the power 5. I'll use this as a template. So we have 3 times 4 to the power 2 over 2 factorial 10, plus we have x to the power 15, 3 factorial 4 to the power 3. Alright, let's do next problem. Oh, was it 5? We have f of x. Now, here we're going to recall the fact that e to any power is that power to the power n over n factorial. Now when you multiply it by 2, this becomes 2. And when you multiply it by x over here, you can surely multiply by x over here. Right, that's not a problem. So let's see what we get by doing this. After we set star to be equal to just x squared, we get 2x e to the power x squared equals 2x sigma x squared to the power n over n factorial. Now, we've done this before with just regular power series, we can bring that x inside. So we have 2x times x to the power 2n over n factorial, and now this x can be combined with this expression, like using the properties of exponents, and this is our answer. So this time they ask only for the first 3 non-zero terms, so the first non-zero term will be 2 over 0 factorial x to the power 1. Second one will be 2 over 1 factorial x to the power 3. Actually, it's pretty straightforward here. So we have 2 over 0 factorial, that's just 2, plus 2x cubed plus x to the power 5. All right, let's do problem number 6. What we have here so again, our starting point doesn't have to be, what are we doing here? First 3 non-zero, so we can do it by hand, technically, right? So we can manually compute A1, A2, or rather A0, A1, A2, using this formula. However, what we want to do instead is we want to recognize the pattern here. Here I'm going to take out 16x cubed over 3, as it doesn't, we can easily handle things like that. And here we have 4x to the 4 plus 1 to the power 4/3, and I want to inspect our list here to see if we have anything to match that pattern. And I do see at the bottom here we have this formula. I'm curious if it works for non-integer values of k, but that's the only thing that matches here. So we have, I'm gonna copy it over here. So we have 1 plus something to the power k, or let's make it n, or k is the right thing, right, is equal to 1 plus k this, plus k times k minus 1 this, plus, and since we only need first 3 terms, we don't really care about what the other ones are. So if in this formula we choose our star to be equal to 4x to the 4 and k to be equal to 4/3, then here's what we're going to get. we're going to have negative 16x cubed over 3 times, in here we have 1 plus 4/3 times 4x to the 4 plus, here we have, let me rewrite this in a better way here. So we have plus 1/2 times 4/3 times 4/3 minus 1, it's 1/3 times 4x to the 4 to the power 2. So here it was to the power 1, here it is now to the power 2, and so on. So again, we're only looking for the first 3 terms, so there is no need for us to write more than what we are asked. And here I'm just going to make some space to put the equal sign, and continuing, we're going to distribute this term over. So we have negative 16/3 x cubed, and now we're going to have negative, and we have a lot going on here, so we have negative 16/3 negative 16/3 times 16/3 x going to be to the power 7. We're going to have another negative 16/3 times we have 4 cubed divided by 18, so I just collected all these terms. So this is 4 squared times 4, that's 4 cubed, 2 times 3 times 3, that's your 18. And x will be to the power 8 plus 3, 11. And there is more, right? So this is what we have. Is this the best way? Let's see. I don't know, actually. Let's type this up. But I think the solution here will be slightly different, because I noticed that there is we could have done it by like integrating this series. It seems like it. There is that pattern, but it doesn't matter. I have 4 to the power 5 over 3 times 18 x to the power 11, and let's see. Let's check the work real quick. So the pattern is fine. So the only thing I would just put factorial over here as a part of the pattern. Now plugging everything in, we have negative 16x cubed 1 plus k times 4x to the 4 plus 1/2 4 over 3, so 4/3 times 4/3 minus 1 is 1/3. Here we have 4x to the 4 squared, so we have x to the 8 plus 3, 11, so the powers are fine. Now the coefficients, we have negative 16/3, and we have here 4 times 4 over 3, that's also 16/3. That's fine. Now here we have 4 squared times this 4, that's 4 cubed, times this 16 in the numerator. In the denominator we have 3 times 2 times 3 times 3, that's 18. Have no clue why this is the wrong answer. I'm going to pause here for a second so I can figure this out so it doesn't count against our attempt, and then we will continue. The mistake that I actually made is a silly one. When we're trying to use this formula, like this formula right here, since we have the whole thing is in the denominator, our k is actually negative 4/3. Now, once we fix that, things actually work out nicely now. So we're gonna have, not nicely, but it is the right thing to do. So we're gonna have negative 4/3 here. We're going to have negative 4/3 here, and negative 4/3 minus 1, it's actually negative 7/3. And what's going to change? The sign here is now positive, and here we're still going to have 4 to the power 3. We're still going to have 16/3, but we're also going to have this 7 over here coefficient. So to adjust the answer, we're going to put plus over here, and we're going to change this. It's still going to be 4 to the 5, but we're also going to have times 7, if I'm not wrong. And that should fix it. That should fix it. So let's try. Yeah, that's correct. However, this proposed solution is horrible. Don't follow it. It makes no sense. Like differentiating when you can avoid it, it just makes no sense. All right, let's move on. In here we have a function, and we're going to do the suggested identity. And we're going to recall the Maclaurin series for cosine. and we're going to set the star to be 6x, and now we're going to continue writing this. So we're going to have 1 minus, and instead of the star we'll put 6x, and we need to write the first 4 terms, so let's start writing it. When n is equal to 0, we have, well, actually, let's simplify it first. That's all there is to simplify for it now. And now we're going to start writing the term. So we have 1 minus. When n is equal to 0, we have 1 over 0 factorial x to the power 0. When n is equal to 1, we have negative 1 6 squared over 2 factorial x squared. When n is equal to, how many terms do we need? 4. We have negative 1 to the power 2, so it just becomes positive 1. 6 to the power 4, x to the power 4 over 4 factorial, plus, we'll continue, plus we have negative 1, 6 to the power 6, x to the power 6 over 6 factorial, and we're going to have to go one more because this one will cancel this one, and we need 4 non-zero terms. So we're going to end up with 6 to the power 8, x to the power 8 over 8 factorial, etc. Now, distributing this cancels this, and now we distribute this negative 1 over, so we end up with 6 squared over 2 factorial x squared minus 6 to the 4 over 4 factorial x to the 4 plus 6 to the 6 over 6 factorial x to the 6 minus 6 to the 8 over 8 factorial x to the power 8, etc. So we have 6 squared over 2 factorial x squared minus that plus that minus that and we finished the first part of the homework. Now we're going to continue to the second part, so it's going to be a very long homework. Well, actually, there you go, this one is good, and now this one. So number 8, find the radius of convergence So when looking at this question, let's acknowledge that we're not asked to find the interval of convergence, we're asked to find the radius of convergence. And what we would use here is this. 1 plus something to the power k is equal to 1 plus whatever, right? So we're not looking at that. What we're looking at is that this condition. So the absolute value of that something must be between -1 and 1. Now, in our case, that something is equal to -9x cubed. So the condition that we have to satisfy in order for this series to converge is now written like this. And solving this inequality gives us this. And x is therefore here. So if you look at this interval, it starts at 0 and it goes to here and to here. And it may or may not converge at this point. But whether it does or doesn't affect the fact that the radius is equal to 1 over cube root of 9. So the answer to this question is just 1 over, or we can just be fancy, 9 to the power -1/3. This is exactly the same as 1 over cube root of 9. Definitely don't look at this solution. It's insane. Here we're going to take a look at this table, and we know that ln of x, or ln of something, or I guess ln of something plus 1 will be that something minus something squared over 2 plus something cubed over 3. So this is what I'm getting out of that formula. But what's most important here is that all that is only the case when that something is between -1 and 1. This is the main message here. This is where we're going to get our interval of convergence. So in our case, that something is 3x squared. So setting the absolute value of 3x squared to be less than 1 will result in this inequality that can be solved like this. Now, it may or may not converge at the boundaries. So it could be a non-strict inequality, but the radius is still 1 over square root of 3. So it's 3 to the power -1/2. Definitely don't look at this solution. Technically it's true, but we now have higher level knowledge and we don't have to do everything by hand. Another one of this type of problems. we're going to recall that arctan of something is something minus something cubed over 3 plus something to the power of 5 over 5. And again, all of this is only true when absolute value of that something is less than or equal to 1. I'm looking right over here. And we're going to set our something to be 2x. So absolute value of 2x being less than or equal to 1 means absolute value of x is less than 1/2. X is between negative 1/2 and 1/2. And the radius is just 1/2. Same thing. We know that arctan converges to what the series representing arctan converges to arctan for all the values between negative 1 and 1. So I'm just going to write it here. Negative 1 to the n x to the power 2n plus 1 over 2n plus 1. This only makes sense when the following inequality is satisfied. So in this problem, the star is 4th root of x over 7. So if you want the absolute value of 4th root of x over 7 to be less than 1, that means that's an interesting one, actually. X is between 0 and 7 to the power 4. X cannot be negative here. So I'm wondering if the interval of convergence... So because of the constraint on x here, normally you would say the interval of convergence is from negative 7 to the 4, but x cannot be less than 0. So technically this is your interval of convergence, but the radius is, I don't know, let's try 7 to the power 4. And even though it's correct, it's technically correct, but x cannot be negative. So let's just move on. Alright, the next problem is number 12. We have a function and for such function we have a formula, and the formula is and whatever the formula is, it's only true when absolute value of x is less than 1, and potential on one side, this is a non-strict inequality, but it doesn't affect the radius. So in our case, this is our star. So to find the interval of convergence, we set up this inequality, and to solve this inequality, we use the algebra. So in real life, I believe this will be non-strict, but it doesn't, whether it is or it is not included, it doesn't affect the fact that this is the radius of convergence. Definitely don't look at that solution. And the last problem, hopefully, if we get it right, can be expressed like this. And we're going to recall this formula. But this formula only works when this expression in absolute value is less than 1. So in our case, we have the star to be equal 6x to the 4, and the k is equal to -1/3. So to find the interval of convergence, we plug that in, and this is the equation that, rather, inequality that we have to solve. And to solve it, this is what we do. So the radius of convergence here is 1/4√6, or 6 to the power -1/4. And we finish this homework. If you have any questions, please feel free to reach out.